You could hit F11 if you really wanted to.
Yeah.
There we go.
There we go. Now I can actually start. All right, I'm Tanner. So, I was introduced. Started out man on both social media. It's just an anagram of my name. So I'm presenting cryptography for us mortals. Originally, it was going to be more of like a guidebook for how to implement all of this, but I got some feedback, and they were like, "You should probably do something that's like 101 first, and then later on talk about it." So that's what this became. So like I said, it's a basic crash course in modern practical cryptography. So what I mean by that is it's not going to be anything about like World War II with like the, what was it called, Enigma machine and whatnot. It's going to be stuff that we actually use today and stuff that is generally considered secure. And target audience is kind of just anybody who is genuinely interested in cryptography but hasn't really delved into it. So that kind of describe y'all. Sweet, nailed it. This is not a manual, so it's not, consulting this is not going to give you the magical crypto powers, you know, to implement everything securely. This is more of like a jumping off point. It's not all inclusive. I'm not going to talk about every single modern cipher. You know, there's too many of them, and every single modern cryptography primitive or whatever. It's also not mathematically inclined, so I'm not going to go into the mathematics behind like the AES cipher or whatever and how that works and why it's secure. I'm just going to talk about how to use it and how to use it safely. And not going to be explaining how most of this stuff works, just how to use it. So I really like this quote. That's one that's I've kind of kept in mind for a pretty long time. Essentially all it's saying is that anybody is smart enough to come up with something they themselves cannot break. This is a general theme inside pretty much every crypto community, in that always, if you want to make a good algorithm, a good secure algorithm, you have to have other people look at it because you're going to design around your own knowledge and not everyone else's knowledge. So I also referenced Bruce Schneier a couple of times later on in this presentation, so keep out for that. So cryptography solves a couple of different problems for us. Generally, they can be boiled down into three groups of privacy, authentication, and integrity, and usually the last two kind of go hand in hand. Privacy is pretty straightforward. It's keeping our data secure against all of the bad guys of the world. So let's say you want to keep your private messages between you and your significant other, or you want to communicate with a news source securely and then keep your identity from being leaked. Or big websites that store credit cards and whatnot will use encryption to keep it, so if their databases are compromised, it's not the end of the world. Also hard drives for, on my laptop personally, I have it encrypted so if it's ever stolen, nobody can look through it. It's also useful with corporate espionage, companies kind of possibly look at what each other are doing and try to get through all that to get trade secrets and whatnot, and I have no experience with that. Also, I generally don't talk about how to secure stuff from governments because I have no idea. I don't think anybody really does. So that's outside the scope of any talk I'm going to give. So authentication, most of us should have a general idea of what authentication is. You know, it's this random person is claiming to be Ed, for example, and I want to prove that it's actually Ed. This can also be used for messaging if you want to prove that a message came from a specific person. It can also be used for voting to prove that this person is who they claim they are and they're actually allowed to vote on something. That's pretty straightforward. Integrity is proving that something hasn't been modified since it was sent or transmitted or whatever. You'll generally see this in the form of an attached hash or signature on it. When I say it goes hand in hand with authentication, usually most of the operations that we do that can provide authentication also provide integrity, in that it says something like, I am Tanner and this message has not been modified, and you can prove that mathematically. Since we have that capacity to prove that it came from someone and it hasn't been modified, they also can't claim that they didn't make that message, which is what non-repudiation is. So if I see a message that is signed with someone's cryptographic key, I can say, no matter what you say, you wrote this, like this is you. And I sometimes refer to the integrity and authentication like combo as authenticity. That's kind of confusing, but I like it. So this section is going to be all about building blocks of cryptography, and it's kind of structured like this thing evolved into this thing evolved into this thing, or in two different branches, or whatever you want to think of it like. So first what we're going to talk about is one-way functions, and they're exactly what they sound like. It's something that it's easy to compute. So for example, if you have two really big prime numbers and you smash them together, multiply them or whatever, that's very easy. But to get from that big number composed of two other prime numbers to the original numbers, it's very hard. It actually provides a basis for a lot of our cryptography that we'll talk about later. A special case of one-way functions are what's known as trapdoor functions, which, kind of think about it, if you were like crawling about a trapdoor, you know where the trapdoor is, so you can pretty easily, open back up and go down there. But somebody else walking into the room might not know where it is, so they can't go the other way. It's when you have a secret information that makes it easy to reverse the operation. So for the two prime numbers, if I tell you what one of the primes is, you can really easily find the other. You just divide them. So, you have any questions so far, or is that just sweet? So cryptographic hashes are essentially just functions that turn any size block that you want of bytes or numbers or whatever, and turn it into a fixed length output. So most of them will be defined over something like a pretty small output, like 256 bits, for example. So cryptographic hashes have a couple of different properties in order to be considered secure and be used for cryptography. First one is that the same message should always result in the same hash. So if I encrypt the message hello world twice, I want every single time for those two things to have the same hash. Otherwise, it's pretty much useless. Usually we want them to be quick to compute for our messages, so even if I have a absolutely gargantuan file, it should still be fairly quick to turn that into a hash. One of the most important properties of a good cryptographic hash is that a small change in the input message results in a giant change in the hash. So you might take that hello world and you might change the D at the end to an F. That's going to completely change almost every single digit inside your hash. And that kind of makes it easy for two things. One, if you're like looking at it from a glance, you can tell the two are different. And then two, it makes it so that you can't really approximate where a change is going to happen and all that. They also need to be infeasible to invert, which is why it's a one-way hash. So if I give you just a hash, you shouldn't be able to tell me what message created that. And as a side part of that, you shouldn't be able to find two different messages that have the same hash. If you can do that, then that's called that hash has lost its collision resistance, which is what happened to MD5 that I have listed up there. So a couple of different hashes that you might have heard of. Blake 2, that one's a pretty recent one. That was designed a couple of years ago, and it's a special hash that I'll talk about later. SHA-3, so you've probably seen SHA-1, SHA-2, and SHA-3. Those are kind of iterations of the same idea. It just stands for Secure Hashing Algorithm. Most people wouldn't recommend using SHA-1 anymore, and SHA-2 is on dicey ground, and I'll explain why in a little bit. So what do we use hashes for? First thing, probably the most common use, is just integrity of files. So you've probably seen this when you're downloading like a Linux ISO or something. It'll have the .SHA-SUMS or whatever file, or it'll have a .MD5 or something. And when you download that, you calculate the MD5, and then you compare it to the MD5 that you download from the web server. This is not to guarantee that it hasn't been like maliciously tampered with. It's only to guarantee that there was no error in transmission from point A to point B. Two, they're all often used for password storage. We've all probably dealt with this before, where you have to have a way of verifying someone gave you the right password. You don't want to store the passwords just as they are in your database, because if somebody gets access to it, they have access to everyone's passwords. And since hashes are designed to be infeasible to reverse, obviously we're going to use that to store them. They're also often used for key derivation. So since keys to the various algorithms I'm going to talk about are generally defined only for one size and no other size will work, and since passphrases, which are things that we can actually remember, are often various links, hashes are an ideal candidate to convert between the variable length passwords and fixed length keys, and also going to talk about that. It can also be used for authentication. So if you have a message and you attach a key to it, like some secret key that only you and one other person knows, well, nobody else can calculate what that hash is going to be without that key. Because of that property of you shouldn't be able to find two messages that have the same hash. And you can use that to verify that somebody is who they're claiming because they have access to that secret key. So hashing passwords are kind of a special case. The old wisdom used to be that you would just filter it into a standard hash and you would store that, and that was pretty much it. That had a ton of problems. One of the bigger ones is that a lot of these hashes were designed to be fast because they're meant to act on a lot of data, and you don't have to wait for 3 hours to make sure your file is safe, or not safe, is intact. And nowadays, a lot of like the GPUs that you can buy on like the market, you can hook a bunch of them together, and you can get billions of passwords per second, and you can just guess them and compare hashes. So a lot of times, people recommend now using a key derivation function. Essentially, they're different ways to, they're just like a list of steps of how to apply this hash this many times or include these variables or whatever. And it's just meant to increase the complexity of calculating that and also make it so that the, let's say two people have the same password, they should have different hashes stored in the database, otherwise people would know, hey, these two have the same password, if I get one, I got the other. And they do that by usually adding like a little bit of randomness in there. A couple of examples of those, Argon 2, which is a recent one that was meant to be GPU resistant. bcrypt, scrypt, those two are used fairly often. Usually bcrypt is the more web one because it just does it all for you. You don't have to remember any cost parameters or anything. Then a really old one is the password-based key derivation function, or PBKDF, which I almost never remember on the first try. That one is more of just the way it kind of works is just repeating over and over again. And there's some additional stuff in there that I don't really care about, to be honest. But so authentication with hashes. I talked about this a little bit. We usually call this a message authentication code, or MAC, which is how we refer to it for the rest of the presentation. Everybody that's involved in the communication that wants to verify if the message is authentic has to know the secret key, because the way they work is by combining the message with a singular secret key, like I said earlier. This kind of limits their use in like group settings, because everybody who has that key can not only verify every message, but they can also create new messages that are verified. So usually this will be kind of like a one-to-one, like two parties that are communicating. This is often also used with one person, where only they know the key, and then they are storing it somewhere else that they don't trust. And then when they get the data back, they'll verify that it hasn't been changed. So essentially, they're just proving that it came from themselves. It's a cool little usage there. So the way I've kind of structured this, every section will have what the stuff is in the section, and then what are the problems with it. And then I kind of explain like how to get around some of the problems. So problems with some hashes are what's called a linked extension attack. So for certain hashes, the way they were designed is the when you feed data into it, it's just modifying an internal state. So this could be just like a big byte array or something like that. And when you feed data into it, it's defined that these certain things change, and then when you're done with it, you basically just spit out the internal state, and that's your hash. And that's how a lot of older ones were designed. So if you have the hash of something, you have what the internal state was before you had finished it. So let's say that you have like an MD5 hash, for example, and you're like, well, I want to add the text foo to it. Well, you can just perform the same defined like a transmutation, I guess you can call it, to that same byte array, and then you can spit out a new value. You can only go one way with that, so you can't like try to go back in time and take value off. You can only add stuff. So this can become a problem with certain like naive implementations of message authentication codes. So when I said earlier that you combine the key with the message to change the way the hash works, a lot of people used to do it that they would basically just append the two. You would have the key and you would just stick the message on the end. So this becomes a problem, one, because if you know the hash of the key, you can do any message you want, because you can just keep adding more and more data to it, and it's going to be a valid hash. It also becomes a problem that if you know what the original message, how long it was, you can add more stuff to it. So let's say that I make a request to, this is what happened to Flickr. If I make a request to Flickr's API and I have like, and get this thing and set this parameter, if somebody has the hash for that query, they can just add and delete whatever they want onto the end of it, and that's going to be an authenticated request. And that happened to them, I think that was 10 years ago now. I don't know, that was a while ago. So it's kind of an example of how naive implementation, some of this stuff can kind of bite you. So not all hashing algorithms are vulnerable to this. It's only a certain family of hashes. MD5 is, SHA-1, SHA-2 both are. SHA-3 is not, and that's because it's a completely different family than SHA-1 and SHA-2. They have the same name, but it's completely different constructions. And then Blake 2 is specifically designed to not be vulnerable to this. That's kind of neat. So a lot of smart people way back when were looking at how a lot of people were doing like the SHA of key plus message, and then that was screwing people up. So they came up with a special way of combining them so that you're no longer vulnerable to that. And that's called it's called HMAC, or hash-based message authentication code. The simplified version is you essentially just take the hash of the key concatenated with the hash of the key concatenated with the message. And what that does is kind of make the data that you're adding to it unpredictable, and you can't stick more data on the end of it, or else it's invalid. Some other algorithms were designed not to need this. Blake 2 is one of them, where it's actually has a separate mode that's defined for this, where you just feed it in a key and it changes the whole way the hash works. So you guys still good? Fantastic. And I just did like a little common hashes that you might see around output size and all that. It's not super important to know all this. Generally, you just need to know that, oh crap, that's what I wanted. Generally, just need to know, avoid MD5 and SHA-1. SHA-1 has kind of lost its collision resistance. Some Google researchers demonstrated that a little while ago. You might have heard of it. It's called the Shatter attack, I think, where they had two PDFs that were, one had like a blue background, one had a red background, and they had basically just added a bunch of data on the end of one of them that was calculated so that it would have the same hash as the red one. So no longer secure to really use that. SHA-2 hasn't really been cracked yet, but you should probably avoid it because there's better options out there now. It's not broken yet, but attacks only get better over time, they never get worse. So you should probably move on. I would personally recommend using SHA-3. It's implemented in most crypto libraries, and it's fast, not vulnerable to a lot of the stuff that I talked about earlier. These two are also interesting in that you can define how long you want your hash to be, and then everything you produce after that will be that length. So you could construct one Blake 2 object and say this should output 32 bytes, and then you could have another Blake 2 object that outputs 64 bytes, and so that gives you some like flexibility with implementing your protocols and whatnot. So a couple of don'ts: use MD5 for anything other than basically just a checksum. It's not to say don't use MD5 at all, but it has a very specific use as a super fast, low cost way to verify that it just hasn't been changed in transmission. That doesn't mean it hasn't been maliciously replaced or modified. It just means that there was no random error while it was being given to you. Don't do the SHA of key concatenated message for the reason I talked about earlier. And HMAC MD5 is not broken yet either. But again, like I said, attacks only get better, they never get worse. And a lot of people are saying, well, it's not broken yet, it's right on the horizon. So yeah, avoid that. Do use Blake 2 or HMAC SHA-2 or SHA-3 if you're going to be doing any sort of message authentication codes. Those haven't been broken yet and generally pretty fast. So yeah, let's get into encryption and whatnot, not just hashing, because hashing is a little bit boring sometimes. So there's two different kind of branches of cryptography that usually get talked about. There's symmetric and asymmetric. Symmetric cryptography, exactly what it sounds like. It's when all participants have a shared secret, and that shared secret is used to go both ways of whatever operation you're performing. So if you're encrypting, the same secret is used to encrypt as is used to decrypt. If you're validating a MAC or creating a MAC, the same secret is used to create, and then the same secret is used to validate. This means that anybody with the secret can perform all the same operations. So generally it's not used in like a widespread group setting. So one of the first like variants like of modern cryptography that used symmetric key cryptography was one-time pads. Essentially what they are is just a big block of data that is as long as your message, and every character of it is just combined together using either the binary exclusive OR operation. We all familiar with that? I didn't put a slide in here. Sweet. Or you can also do like modular addition of letters. So that's when you convert like a letter to a number, and then if it's over 26, you round it, and you go back to 1 or whatever. Old one-time pads would do stuff like books. So you would have like a predefined book that you both agree on, and then you would combine the two and go down the line. That was vulnerable to cryptanalysis because the patterns in the key were pretty predictable, because English is predictable. And if you can predict the key, then you can predict the rest of it, you know, and then you can decrypt the object they're trying to keep secret from you. Secure one-time pads use random keys, and I don't just mean like pseudo-random, I mean like generated from like truly unpredictable phenomena. So that could be like if you're a masochist, dice rolling. You could also do like there's various hardware random number generators that base it off of like thermal weird physics stuff. Basically, in order for the security of a one-time pad to hold up, it has to be random. So I did a little example of a one-time pad by hand. That's always fun. Basically, I had this key here that I generated randomly. Here's my text. I just converted all of them into numbers, and then for each one, I just added the two numbers together and rounded. That's ciphertext that I got. So, why one-time pads are great? It's impossible, full stop, to crack without the key, assuming the key is random, obviously. The reason for this is that every decryption is valid. So if you find two different keys, like I did here, we have the real key and then we have the secondary key. There's no way to tell which of these messages is actually what I was trying to say. So you could find, like for example, let's say that you encrypted the phrase, we attack at dawn with this, and then you had a key for that. If somebody's going through and brute forcing keys, they could also find the message lunch party at 6 or whatever. And there's no way to decide what they actually meant. They can be done by hand pretty easily. Some like Soviet spies used to kind of do this with paper that was meant to be burned, and they just had pads. They would literally just do it by hand to transmit messages to each other, so that's kind of cool. It's also very fast and simple. There's not really much to implement if you're going to write it into software. Not much to get wrong. They actually kind of suck though, and we don't really use them. Because the key has to be, like I said, truly random and at least as long as your message. And it also cannot be reused. And the reason for that is if you reuse a key, then you can just do the same operation to two different ciphertexts, like combine them together, subtract, or whatever you want to do, and that'll give you what the key was. And then you can use that to decrypt either of them. The key also has to be distributed securely before sending any messages. Obvious reasons for that, but it's kind of hard to do in real life. You know, you're pretty much limited to just walking up to someone with a piece of paper and be like, here it is. The messages can also be altered pretty easily. So if I'm like an attacker of some sort, and I see this Q here and I change it to an R, it's going to change whatever your message is. And surprisingly, that can actually be pretty useful, even if you don't know what the original message was. For example, if they had the we attack at dawn thing, and they could potentially change like the end part to be whatever they wanted. Well, not whatever they wanted, but something random that you wouldn't be able to tell. This has been used, that kind of attack has been used with various APIs where they can take a guess at where a value will be in the encrypted string, and they can change it, and they can sometimes get that right and trigger some different event. I talk more about this later on. So, still good? Sweet. String ciphers are essentially an approximation of a one-time pad, but instead of having a fixed key that's as big as your message that you have to haul around and give to other people, you have a short key that is used to initialize essentially a random number generator that generates the key that you're going to use for the one-time pad. And the key that's generated on the fly we usually refer to as the key string. So, upside to this is that they're generally pretty fast. A lot of these, there's no super complex function yet to put in place. There's no different modes of operation that you can do with it. It's just, here's the key stream I'm generating, and I combine it with my message. Same problems that apply to one-time pads kind of apply to stream ciphers, in that if you reuse the same key, it'll generate the same key stream. If you reuse the same key stream, then your security is completely broken because of the previous attack that I talked about. So what we do is we typically generate a special number and combine it with the key. And this could be like either, it depends on the algorithm. Most of them will have like a specific way that it changes how it operates. Like you're not just smashing the two together, the algorithm is taking inputs from both of them. We usually call this a number used once or a nonce, which makes its purpose pretty clear there that do not use this twice. Nonces don't always need to be random, they just need to be unique. Some protocols will tell you to start with a counter, and start with like 1, and then every single message you just increment that, and that guarantees that all your messages will have different nonces and therefore different key streams. They can also, for some algorithms, if the nonce is big enough, then they'll say, yeah, just generate it randomly. Because if you generate big enough numbers, they're probably not going to repeat. They don't need to be kept secret. They're usually sent along with the ciphertext. So you'll have nonce at the front, and then you'll have ciphertext afterward, and that's how the other end is able to decrypt everything. So block ciphers are the other kind of cipher. They're pretty different. They operate on fixed size blocks, so instead of having a long key string that can be however long you want it or however short, they operate on very defined sets of bits. And AES, for example, will only operate on 16-byte blocks. You put a 15-byte block in there, it's not defined. Or 17 or whatever, it's not defined, so you can't do that. If you have a smaller message, like if you have a 14-byte message, you'll generally pad it out, so you'll add bytes to the end of it to make it up to 16. They don't have really a concept of larger messages, and I included something pretty easy down here, you know. Combine the block and the key, your ciphertext, combine the ciphertext and the key, you get your block. So some examples of this are Randall, or AES, which stands for Advanced Encryption Standard, kind of defined by a competition several years ago that won a bunch of cryptanalysis. There's Blowfish, which around the same era. That one's now considered broken. It has a small key, small block size, so try not to use that. Twofish was an upgrade of Blowfish. Then there was the data encryption standard, which was the predecessor to AES, which is now considered completely broken. So problem. What happens when I have big messages and I want to use a block cipher? Because like I said, it's only defined for set blocks. A bunch of nerds came up with a way to apply block ciphers to larger messages, and they're called modes of operation. Essentially, it's just a list of instructions for what to do. So the most basic one is called electronic codebook mode, and all you do is you take your big message and you split it up into the fixed size blocks, and then individually you apply the block cipher to them. So super easy to implement. Identical blocks are going to produce identical ciphertext. So if you have two blocks of complete zeros, then they'll have the same ciphertext, which means that patterns inside your plaintext will be recognizable in the ciphertext. That's kind of demonstrated with this image here where we have tux here, and then we have encrypted tux, electronic codebook mode. And while you may not be able to tell all the details, you can tell what's behind it. So generally you want to avoid that. So to kind of fix that, we had to add some form of permutation between each block and each operation. So one of the most common ones is called cipher block chaining, where essentially to encrypt, you first generate a random first block, and then you combine that with your first block of your plaintext. So usually that'll be through like XOR or something like that. And then you encrypt it, and then the ciphertext from that block is fed into the operation of the next one. So you'll take the plaintext, you'll combine it with the previous ciphertext, and then you just keep doing that as you go down the whole thing. So that gets rid of any patterns, because the second you run into a change, the rest of the whole thing will be completely different. So here's tux, and then here's tux encrypted with a cipher block chaining mode. That's kind of neat. So that first block that I talked about that has to be randomly generated, because you have to have something to combine the first plaintext block with. It's called an initialization vector. They have to be random. That's what kind of separates them from nonsense usually. They must not be reused, and this depends on different modes of operation what will happen. With CBC, if you reuse an IV, then as long as the first plaintext, or the two different plaintexts you're comparing are the same, the ciphertext will also be the same. So that can show you patterns in relation to two different plaintexts. So for example, if you had this tux image and then you had like the GNU devil, is that what they have? Anyone know his name? That's kind of sad. Maybe the Go Gopher. The first part of it will be the same here, but then once it hits a difference, the rest of it will be different. Does that kind of make sense? It's not a break of it. You know, it's not quite as bad as you're using it with a stream cipher where they can decrypt the whole thing, but it could tell them some potentially useful information. IVs are also not private. They're generally sent along with the messages just like nonces, and they're required for decryption. With CBC, though, if you don't have the IV, you won't be able to decrypt the first block, but every block after that will be fine. And the reason for that is because we're propagating the ciphertext and not the plain text. Does that kind of make sense there? Cool. So, a couple of people thought stream ciphers are cool and we want to make block ciphers operate like them. So they came up with these modes of operation. Generally speaking, the way they work is they just add a counter to the encryption mode. The most prominent one is called counter mode or CTR. Essentially all that does is you start out with a random value and a counter appended to it, you encrypt that, and then you combine that with your plain text. And then you go to the next block and you increment the counter, you combine that, or you encrypt that, then you combine that with your plain text, and you just keep going. It's kind of like codebook mode, except for instead of encrypting our plain text, we're encrypting what amounts to a unique random value. So here's like kind of a diagram of that. So you have your counter and then your nonce that are combined together, and then you split your message into blocks. Every block you encrypt your nonce and counter pair, and then you combine that with your plain text, that gives you your ciphertext. You just go and do that forever. So that kind of turns it into a stream cipher there. So, quick note on keys. I use the word keys a lot. They are distinct from passwords, and that what I said earlier, how passwords are variable length and they're usually human memorizable. Keys have to be random and they're fixed length, and it's really hard to remember random data. 32 bytes of random data, you're just get out, you're not going to remember that. Usually we derive keys from passwords before we do any encryption using the key derivation functions I talked about earlier. So, problem with just encrypting. There's no authentication at all with most of these encryption algorithms. So there's no protection against modification. So I really should turn that off. So if I can guess where a value is within your cipher stream, then I can potentially modify it, which can break the rest of your protocol if you're relying on that data being unmodified and trusted. Solution, combine it with the MAC. So general way you should do it is encrypt your message first and then calculate your MAC over the ciphertext. And then you just append the two. So you'll have your, usually the way you'll do it is you'll have your MAC first, and then you'll have your IV or your nonce, and then you'll have your ciphertext. Generally, it's recommended to use one key for your cipher, another key for your MAC. The reason for this is to prevent against like some unknown correlation between the encryption cipher and your MAC algorithm that expose weaknesses that we just don't know about yet. So maybe it turns out that some operations within your MAC undo certain operations with your encryption, and now we can't predict that, and that might lead to a break. So we generally say have completely different ones. Also, this is very important. Always verify your MAC before decrypting. Errors in the decryption process can expose you to weaknesses sometimes. So before you do any sort of decryption, make sure you trust whatever you're decrypting. And the only real way to do that is with the MAC. So that concept is a little bit separate than authenticated encryption modes, which you might have seen this like abbreviated AEAD, or authenticated encryption with additional data. Generally, they operate pretty much the same way as encrypting and then adding a MAC, but it does it all in one step. Usually it has a concept of what's called associated data, which is data that is not encrypted at all. It's public, but it's verified to be non-modified. So we know it's authentic. This is generally stuff like packet headers or whatever your preceding information for the rest of it is. So you might have something that says the length of your message, which is not really secret data, but you want to verify it's correct, then you'll include it in the associated data and send it along. Two examples of authenticated encryption schemes are Cha-Cha-20, which is a stream cipher developed by Daniel Berenstein, which he combines it with another algorithm that he developed called Poly 1305. You don't really need to know those two, just recognize them. So if you encrypt something with this algorithm, and then all you have to do is decrypt it, and that operation will tell you if it's authentic and if it's been tampered with. AES-GCM is so GCM is a mode of operation for any block cipher. Generally, you'll only see it for AES though. And I personally don't understand how it works. If someone wants to have a discussion on that at some point, do their own research and compare notes, that'd be great. But it does the same thing pretty much as Cha-Cha-Poly. GCM also converts AES to a stream cipher. That's another thing that you should probably know. Yeah. So here's a couple of common symmetric ciphers. AES, which is a block cipher, takes a 128 or 256-bit key. I think it operates on, well, I know it operates on 128-bit blocks. Cha-Cha-20, or Salsa 20 was the predecessor to that, is a stream cipher. It can take either 128 or 256-bit key. And then Twofish and Serpent were other submissions to the same competition that AES came out of. And generally they haven't received quite as much scrutiny as AES, but they've received a lot of scrutiny. So those are kind of neat. Don't use electronic codebook mode. There's really no reason to anymore. You might possibly use it if you have small data and you're constrained on resources, but in most cases you really shouldn't. Don't use Blowfish or DES or some random thing that your friend said was kind of cool, you know, something that they made themselves or whatever. You can play with them, obviously, on your pet projects. I'm not saying never use them ever. I'm just saying if you're doing something important, don't use them. Also, don't use passwords as keys. I've seen this a lot where an encryption function will take a key and people will think, well, I'll just pass the string password into it. That doesn't work. You'll wind up with a lot of weird problems. So use a key derivation function first. If you're going to be writing your own encryption code, use AES-256, CVC, or CTR with HMAC SHA-256. That's my recommendation because most libraries are going to have both of those implemented. Use two different keys for the HMAC and for the cipher. The other reason I recommend AES is that it's usually hardware accelerated, so you can get like just insane throughput on it. If you have the option, I would recommend using Cha-Cha-20 Poly 1305 because it's one function, one key. You don't have to worry about anything else. If you want to add in associated data, it's pretty easy to do. It's also really fast. That's why it's kind of being chosen for like the new TLS ciphers and whatnot, which is used to secure HTTPS connections. Also, like I said, always derive your keys from passwords. Or if they don't need to be remembered, like they're going to be only used by computers, you know, people are never going to touch them, you can generate them randomly. That's fine too. So, any questions about symmetric cryptography so far? Cool. Asymmetric cryptography. So, a lot of people have trouble wrapping their minds around some of this stuff. All participants have different keys, and usually it'll be like a key pair. So you'll have your private key that you keep to yourself, you never let anybody else see it. And then you have your public key that can go wherever you want it to go, and you'll share that with everyone, basically. they're mathematically related so that the way they're generated, one usually comes from the other, and they'll be linked together. Instead of max, we usually call it a signature here, and I'm personally not sure why.
What does MAC stand for again?
Message authentication code,
Okay.
and that's when, does that work?
Yeah.
Okay. Yeah. The public.
I think I know why they call them signatures, because so when you try to generate a hash, sometimes you want to encrypt it. But when you're dealing with a symmetric key, then you have the advantage of using like your own private key to encrypt, and they don't have to decrypt it using your public key.
Yeah. I think also like it has something to do with usually your private key is only kept to one person, unlike a Mac where it's shared, like you were saying. So if something has a signature, you can also prove it came from one person. I think that's also part of it. So anyways, the public and private keys are used to go different directions. So public keys are used for encrypting and then validating signatures, and those are separate operations. And then private keys are used for decrypting and also used for creating signatures. Ideally, everybody knows everybody else's public keys. They cannot so far be used to find out the private keys. There's a lot of speculation that with quantum computers that'll be possible. Private keys, on the other hand, can usually be used to derive the public keys. Usually they're kind of stored with the other variables that are required to make a public key. Some examples, so all of these are split into two groups. There's usually, the two common groups are, one's based on integer factorization, so that'll be like the big prime numbers and whatnot, and that's like RSA and DSA. Then there's some that are based on what are called elliptic curves, which are completely different than integer factorization. The benefits of the elliptic curve ones are generally they have smaller keys and they're faster to perform operations with. Not a whole lot of benefits to RSA, more than it's just easier to understand and generally well implemented. So signatures. Like I said, signatures can only be calculated from a private key. Then they can be validated with the corresponding public key due to that mathematical relation I was talking about earlier. If a signature is valid, the message has not been modified, and we can prove that it came from the sender. And signatures are pretty much always sent with the message in question. Otherwise, like, what's the point? So encryption with asymmetric cryptography, messages are encrypted with the recipient's public key. If you don't have the private key, you can't decrypt it, because they only go one way. If you have multiple recipients of the same message, you essentially have to encrypt the message once per recipient, which can get a little tedious. So just a quick bit of key sizes, because I see a lot of questions about this. Most of these algorithms will let you pick a key size. RSA in particular is kind of infamous for this, that it lets you pick pretty much whatever you want. So if you want to try to generate a 65,556 or whatever it is size key, you can do that. It'll let you. It's just going to take forever to do anything with, because all that mathematical operations are just slow. It's not really worth it to do that because there's like diminishing returns. Like the difference between a 1024-bit and a 2048-bit key in terms of security is much bigger than the difference between a 4068 or 96 and then a 8192, for example. The more you do it, the slower it gets, and it gets slower really fast, and it doesn't really get a lot more secure. So generally, you'll want to stick to 2048 or 4096. The other asymmetric cryptography algorithms generally don't let you have that much flexibility. One I was talking about here, Ed 25519, which was also created by that Daniel Berenstein guy I talked about earlier. He's the one that made Cha-Cha and all that. That one only has a 256-bit key, It's just as secure as the RSA ones. It just has a smaller key. Then there's the electric current, digital security, whatever. That's actually a family, but usually when people are talking about that, they're talking about the NSA specifications, which have like a 520 watt bit key, and then 2 other sizes that I can't remember. They're like 128-ish, and then 256-ish. I should probably look that up at some point. I generally don't use them. I use ED 25519 for almost everything. So, one thing that people started noticing is that asymmetric encryption is pretty slow. RSA, the bigger your messages, if you're just doing naive RSA, it can take a few seconds to encrypt big messages. So to speed things up, we generally generate a random encryption key that we call the session key. Then we encrypt that with the recipient's public key, and then we send both of those along, so the encrypted session key and the encrypted message data. Obviously, we encrypt the message with this session key. That's generally how most protocols will be kind of designed, like HTTPS, so SSL and TLS will both use this. The SSH protocol also does this kind of thing. It's the only way to have fast streams. So one of the problems here is the authenticity of public keys. So I said earlier that everybody knows everybody else's public keys. Well, that's not really how it works. There's no real way to do that. So instead, we have to come up with ways to validate that public keys are real and they actually do belong to this person. So there's 2 general competing solutions. There's the centralized public key infrastructure and the decentralized web trust. And I'll talk about the web trust first. Essentially how that works is that everybody kind of gets together and they validate each other's keys, and they basically sign each other's keys as valid. And you'll collect signatures on your keys. So you'll have, like, for example, I might have a signature from Solomon, a signature from Ed, and then a signature from, I actually don't know your name.
Michael.
I might have a signature from Michael too. And then if somebody else sees that and they trust Solomon and Ed and Michael, then they know that this key belongs to me. So over time, essentially, you kind of just build a network of just associates that have other friends that have other friends that have other friends, and eventually we can all verify each other. That's the idea, at least. In practice, most people aren't part of like the core group. That's called the strong set. The people that have all signed each other. Oops. So these things, you'll also see people do what are called key signing parties. I don't know if any of you have ever gone to one. I haven't.
I've heard of key parties, but it's
Yeah.
a different thing.
Generally, you'll get there and you'll like. Generally, you'll get there and you'll provide like a government issued license or something, like photo ID, and then people will be like, "Yeah, that's you," and then we'll sign your key. Kind of cool that works. I haven't heard of any English talk, so maybe devICT should do that at some point. So the alternative centralized version is the public key infrastructure. So generally you'll have a centralized organization called a certificate authority that signs everybody's keys. And then if you trust that certificate authority, then you trust all the people that it signs. This is how most of the web works. The big ones are like DigiCert, Komodo is kind of big. Quite a few. Fun fact about that, there's about 200 certificate authorities that are at the root that control all of it, that are trusted by Firefox on default. So if any one of those is compromised, then they can pretty much issue keys for anything else. So it's kind of the problem with centralization. On the flip side, it's super convenient to just trust these 200 groups to do it all right. And generally it works out, we think at least. So real quick, another part of asymmetric cryptography that's often used a lot is called Key Exchange Protocol. And essentially what that is a way to agree on a temporary key, generally over an untrusted channel. And it does this through a lot of different ways. Diffie-Hellman, which is the only example I have up here, is probably the most common one. And you agree on a set of parameters beforehand, and usually they're just installed in your operating system. You don't have to worry about them. And they're combined with your temporary data, and that is transmitted. And since it's a one-way function kind of thing there, there's no way for this guy to find your private data. And then whoever your target is combines their private data with your data that you've sent them, and they send that back to you. Then you combine yours, and then bam, you have a shared secret. I can explain that one, the Diffie-Hellman specifically. It's actually super easy later on. Just remember to come back to that. So they're typically combined with some form of asymmetric authentication. This is what SSH does, where it'll use RSA to kind of validate that the whole transaction hasn't been tampered with, but it doesn't use RSA to really encrypt anything. So, fun fact there. So yeah, that's basic gist of asymmetric crypto. Things to watch out for in the future is like quantum computers, like I mentioned earlier. There's a lot of speculation that any of them are going to break pretty much all of our asymmetric crypto algorithms. So there's currently a race to have new primitives that are resistant to that. The group that's doing that, PQ Crypto, I think is what they're going by. It's like an email list you can hop on if you want to and see them have weird arguments about obscure cryptography. It's kind of fun. So anyways, here's some gotchas about various crypto stuff. Side channels, which are probably one of the most annoying and one of the ones that people don't really know about. A side channel is any way to get information other than directly attacking the system you're talking about. So this could be like power usage fluctuations. So when your computer's encrypting stuff, it's going to use a slightly different amount of power for every single operation it does. So if you can watch that, you might be able to determine, hey, this is what it's doing. You can possibly determine what the key is or what they're encrypting. Electromagnetic emissions, this was a lot of different things the NSA has done with this one. Like they had a program called Tempest that they can basically like transmit data without being able to tell, kind of thing. But the most common side channel is timing. Some operations take longer than other operations, and therefore you can kind of determine what operations are being run, and from there you can potentially determine what they're doing. Like I said, it's the most common side channel. Generally happens due to key-dependent or plaintext-dependent operations. So let's say like we have some special check when you decrypt data that you check for the word foo somewhere. And if it is, you perform a super long operation. Well, if some observer is watching this go down and they see that you decrypted something and now it's a super long operation, well, I know that your plaintext contained foo somewhere. It's kind of a super simplified example. The most kind of devastating one usually is hash comparison. So in most programming languages, when you compare two strings, the way it works is that it compares the first one to the first character to the second character, or first character to the next string. If they're different, exits immediately. Then I'll go to the second one, if they're different, exits immediately. It just does that until it gets to the end. Well, if the first character is wrong, it's obviously going to return a lot faster than if the last character is wrong. So let's say that you have a hash and you don't know what the hash is, but you can send one to check against that, and you send all A's and that returns pretty fast, and then you send like A and then a B and that one returns slower, and then you can kind of build that out and just slowly enumerate what every bit of the hash is, for example. Google Keysarc, which was a encryption library that some Google dudes were putting together and got this wrong. And they pretty much got big pull requests, big scandal, all that kind of stuff. So when you're comparing hashes just for secure data of whatever kind, generally use like there's almost always a function inside the cryptography library that's going to be like secure equals or constant time equals or something like that. In Go, it's HMAC.equal. I don't know the equivalents in other languages. You can also just write one if you really want to, or you just have it so that it sets a flag and then just goes down the whole thing. I personally think you shouldn't do that, but you can. So earlier I talked about how when you're combining ciphers and MACs, you always want to encrypt first and then MAC. And this has been called the cryptographic doom principle by Moxie Marlinspike. He's kind of like he's the CEO of crypto, or not crypto, wow. He's the CEO of Signal, the messaging app. And he's generally considered very knowledgeable on cryptography and best practices. Anyways, he kind of just states, if you do anything other than verify your MAC before you decrypt the message, it's going to break at some point, just inevitably. So there are several different ways to combine ciphers and MACs. There's authenticate and encrypt, where you calculate the MAC of the plain text first, and then you encrypt the plain text, and then you stick the MAC on the end. There's authenticate and then encrypt, where you calculate the MAC of the plain text, you stick it on the end of the plain text, and you encrypt that whole thing. And then there's encrypt then authenticate, which is the one that you should do, where you encrypt the plain text, you calculate the MAC of the ciphertext, and then you attach the MAC to the ciphertext. If you're interested in, he has a big article on this. It's actually pretty interesting, called the Cryptographic Doom Principle. It's on his personal blog. You can just Google that and you'll find it. It's one of the top results. Another big gotcha is IV and nonce reuse. Just as a general rule of thumb, don't ever reuse them. A lot of people recommend using like a counter, and then that will guarantee that you'll never reuse it. Or if you ever expire your counter, you can just cycle your key or something like that. Short nonces you shouldn't randomly generate, because it just makes it more and more likely the more messages you do that you're going to repeat a nonce. And if you do that, then the two messages with the same nonce can be decrypted, generally. So yeah, this section I kind of just talked about. Someone say something? No, okay, I thought I heard something. This section I kind of just talk about various cryptographic breaks that have happened in the past. Starting with Google Keysar, which was a high-level crypto library. Their HMAC verify function was using just a basic exit early string comparison. So the way let's say that you were using Keysar for your API, and you had like some header variable in your HTTP request that was like authentication tag equals whatever. So what people could do is create whatever message they wanted. You know, it could be delete your account or something, and they would send it to the server, and then they would put just a big string of A's or something like that into the authentication tag, and then they would time how long it took for it to validate, and then they would send like just a ton of messages and average it out or whatever, and then over time they would just keep doing what I talked about, where you just increment a count, or you increment the one closest to the front until you get one that's slightly longer, and then you start incrementing the next one until there's one that's slightly longer, and you keep doing that until you have a valid encryption tag. Which takes quite a while, but also it's something that can be done, so generally if you want to implement constant time string comparisons. So WEP was an encryption protocol for securing Wi-Fi connections. It was created in like 1998 or something like that, so it's old. It used a stream cipher with a 24-bit IV, which is absolutely tiny. And there was one shared key between everyone, you know, like when you go to your laptop, everybody's typing in the same key. So essentially what people would do is they would just sit there and they would wait and collect a bunch of different packets, and eventually the IV would be reused. At first it would take like 5,000 to 6,000 packets was kind of like the old knowledge that you would just know that would work, and then as different attacks like emerged, and there was stuff like forcing the router to make new packets and stuff like that, it got to the point where you can use some tools like Aircrack NG is like the most popular one that can do it in minutes. So yeah, good news that WEP is pretty much phased out now. So the Flickr API that I was talking about earlier, how they fell victim to a hash extension or link extension attack. They were doing what I was talking about earlier, where you have the API and then you have like a value set along with it that's supposed to authenticate that. The way they did it was simplified. They would take their secret API key and they would just stick the request on the end of it. So if you had a valid request, you could just start adding adding your own stuff to the end of it. So you could have it, so it would delete some of their pictures or whatever. And then you would just do what I said earlier, where you change the state according to the rule of the hash and output that. That one caused some people were very upset about that. Just put it mildly. It was actually used in the wild before they could fix it. So yeah, best practices. So I've kind of talked about like a lot of what not to do, but here's kind of what to do if you're going to be writing crypto code.
I've got to head out. I'll catch the best practices though on YouTube, because that seems like a good thing to know. It's a super interesting thing.
Thanks for coming. Alright, so the conventional wisdom is don't roll your own crypto, use already existing libraries. So generally recommended to use OpenSSL for data in transit. So if you have a stream between the two things you want to be secure, use that. Your operating system will usually provide this library for you. It could be like LibreSSL or Boring SSL, or I think Wolf SSL is like the new one. Generally just use that one. If you're going to be encrypting stuff like yourself, typing in the command line, I would recommend GPG, which stands for GNU Privacy Guard, which can be used to encrypt files or emails or messages to each other. It's undergone a lot of scrutiny, so generally considered pretty secure. If you're going to be doing disencryption, then I would recommend using either VeriCrypt or Lux, which Lux stands for Linux Unified Key Setup, I think, something like that. And that's like the Linux version. VeriCrypt can be used on pretty much any OS. And if you need something custom, like these three things here don't fit your use case, then I would recommend using libsodium, which is a cryptographic library that's been developed over a pretty long time. And what it does is take all of like the low-level stuff out. So instead of talking about AES 256 CBC, you talk about a secret box, and you do secret box seal, and then you put your message in, and then it just magically works. It's great. On the back end of that, it uses like Cha-Cha-20, Poly 1305 for that. Uses some of the asymmetric crypto library or algorithms I talked about earlier. If you're gonna be communicating with someone, generally it's gonna do all the best practices for you. It's gonna generate your keys properly. It has an API for doing it all. That's very nice. So a couple of always things here, always do this. Use constant time comparison functions for hashes. Use the different IV and nonce for every single message. Always, always, always authenticate your encryption. So never just encrypt. If you do that, your message is liable to be tampered with. And when you're generating keys or IVs or nonces or whatever you're doing, don't use your programming language's math package, because that one is generally not unpredictable, and if you know like a slew of numbers in it, you can usually predict the rest of the numbers. So you're going to want to use stuff like dev/urandom on Unix systems, or the getrandom system call on Unix. Fun fact about that is behind the scenes it uses, on modern kernels, it uses Cha-Cha-20, like a modified version of that, and it basically just spits out a key stream instead of encrypting anything. So it's kind of cool. You can also use the crypto API on Windows. I'm not a Windows guy, so I can't really tell you how to use that one. I think it's called like Secure Gen Random or something like that.
Do modern computers have some hardware randomness built in these days? Like,
Some servers do, and I think it's starting to become more popular with like mobile devices and whatnot, but generally no. Usually there's special there's actually kind of fun special hardware components called hardware security modules, which are essentially just like a black box that have keys on them or has various encryption functions and random number generators and all that. And you basically just request data from it, and it gives you the encrypted version back, or you tell it to sign something, it gives you the signed version back. And the keys never leave it, and they can't really be removed from it without destroying them. But it's all just in hardware, flash storage. They're actually very interesting. They're also very expensive usually. I think the cheapest consumer ones you can get are like NitroKey has one for like 60 something bucks. Usually they could run you thousands of dollars. So
Cloudflare uses lava lamps.
yeah, they do. Have you all seen that? The Cloudflare lava lamp wall?
I've seen it.
That's pretty sweet. They basically just hash that. So any questions?
No, I'm just gonna update my resume. Cryptography expert.
I'm kind of planning on doing like a sequence of talks that go more in detail on a specific subject. This one was pretty sprawling. And there was a lot that I wanted to include, but didn't really want to stick it in there. Didn't know where to put it.